started. So normally I would be saying good evening, everyone, but instead of evening, we're actually doing this at 4 p.m. In the Eastern time zone in the United States. So I'm going to say good afternoon or possibly good morning for those of you that are joining us from Indonesia at 4 a.m. I thank all of you for being here and for being such dedicated educators. I hope that their teachers and administrators and students appreciate you. But if they don't, we appreciate you here at the Global Math Department and appreciate you being here. My name is Lee Natero, and I will be hosting this afternoon. This afternoon, we're going to be hearing from Dr. Jenny Tsankova about math revolution needed in geometry. We've already had most of you introduce yourselves in the chat window, but if you haven't already introduced yourself, please do so at this time, letting us know what you teach, where you teach, and what your Twitter handle is if you have one. So before I introduce our speaker, let me explain a little bit about how these meetings work. These meetings are recorded and are available approximately 24 hours after the meeting ends. To view the recording, you would come back to the same URL you used to get here today. The Global Math Community prides itself on being friendly and supportive. The chat room is available for topical and general conversation throughout the meeting. I'll catch your questions for the presenter, so don't worry that she won't notice it in the chatter. So our speaker is Dr. Jenny Tsankova. Dr. Tsankova is a full professor of mathematics education at Roger Williams University in Bristol, Rhode Island, and she teaches the mathematics method courses for elementary and secondary pre-service teachers. She is currently modeling lessons, consulting, and providing in-service training for teachers in various school systems in Rhode Island and Massachusetts. Dr. Tsankova's recent research interests have focused on the geometric reasoning of middle and high school students and the integration of international best practices in education and teacher pre-service and in-service training. She's a founder and teacher in a mathematics K-12 after-school program, Number Street Math Academy in Easton, Massachusetts. Welcome, Dr. Tsankova.
Thank you very much, Lee, and welcome everyone. I'm very excited to finally have this talk about geometry. Geometry is a love of mine, and I have noticed that my secondary math teachers have the weakest understanding in geometry. Roger Williams University, where I teach, does not have a geometry course for the secondary math majors. And they come to me with only their understanding of what they've learned in high school. So that has been a challenge for me to help my secondary students. The same thing with the elementary students that come to Roger Williams. On the other hand, I teach in my after-school program students in grades 9 and 10 geometry, and I am trying to make sure that they get what they need to get in their geometric understanding, and as well as kind of follow the rules in their high school mathematics classroom. In addition to that, for the past couple of years, I worked with the geometry team in a vocational school here in Massachusetts. And they had a challenging goal. After they took away vacations and holidays, they were left with 54 days, teaching days for the year, because they have 1 year of teaching and 1 week of teaching and 1 week of shop. So they had to figure out how to teach geometry for 54 days without sacrificing the rigor and the mathematical topics. So we had to sieve through a variety of topics and figure out how to teach in the best way to be able to accomplish this goal. Okay, so here are some key ideas that I'm going to focus today. We're going to talk a little bit about why we teach geometry, when is the best time to teach geometry, and what are the different ways that we need to do that. And looking at the Common Core standards for teaching and learning and the connections to geometry. We're going to focus a little bit on the idea of proof, how we teach it in school, and what are the best ways for students to access the challenging idea of proof. We're going to talk a little bit about the language of geometry and the need for students to memorize a lot of the terms, and sometimes that's challenging for them. And we're going to look at one or two traditional topics that we teach from historical and contemporary perspective. So this is a nice cartoon I found about geometry, because I'm sure you will share my thinking that geometry is the love of two students in a high school. And it doesn't seem to be the most appealing subject to them out of the math strands in high school, while at the same time in elementary and middle school, students really enjoy working in geometry and measurement. So what happens in high school? Is it the level of readiness? Is it the pace? Is it the rigor of the study? And what are some alternatives that we can consider? So here are what some students think about geometry as I interview all the students that come to me every year. So here's Jessica in an honors geometry. She likes to solve problems. She loves algebra, but she doesn't like geometry. And many students would say, I love algebra. And you know that they love algebra because they like to have an equation and work through the equation, and they know the steps, and that's what algebra is all about. And then Madison says that there are too many things to remember, and she doesn't see the point of that. And finally, Matt, a 10th grade geometry kid, he says there's no logic in the proofs. Most of the time you just repeat what is given, or you have to state obvious information like a common side as reflexive property. And looking at these students' quotes, I think that many of them are very valid, and we need to be thinking about them. So on the other hand, what do teachers think about geometry? Many geometry teachers will tell you that students are not ready for the level of geometry that's expected. Geometry teachers, and some of you are, think that when you teach a year of geometry, you necessarily have to teach algebra. So the students have to make connections between geometry and algebra. And now the Common Core standards ask us while we're teaching geometry to do a considerable amount of teaching in statistics, and many of us teach a little bit of trig. So now that students have to do a considerable amount of working in transformations and in constructions, it seems a lot of teachers would like to have some professional development in order to do that, to give it a good brush upon some of the new ideas that they need to teach. Okay, so this is an essential document that I'm sure many of you have looked at. It is Catalyzing Change in High School Mathematics. And this is an NCTM document published in 2018. And there's a part devoted specifically to geometry in a very, I would say, informal way. Geometry means measure the earth. Geometry connects mathematics to life, and ancient people used geometry and measurements to measure land, to navigate the seas, to build. Cathedrals and bridges have been built years ago, and they still stand, and they didn't have the complicated technology that we have nowadays. So this is important for students to see and understand why we teach geometry. When do we teach geometry? Traditionally, in United States schools, a lot of students go through a year of geometry between Algebra 1 and Algebra 2. With the Common Core state standards, several schools in Massachusetts decided to go and teach 9th and 10th grade geometry. So the geometry is taught 2 years in a row, but not every day, maybe 2 or 3 times a week. And at the same time, students are either taking Algebra 1 and Algebra 2, again, not every day. And this has been tried to see whether geometry is going to be better remembered, explored, understood as it goes through an extended period of time, because students need continuous reinforcement. As we all know, in many European countries, mathematics is taught geometry in particular is taught every year. At least 40% of the amount of mathematics is geometry. So students never actually stop learning geometry from elementary to middle to high school. And finally, how we teach geometry and how do we make connections between mathematical ideas, especially the modeling connection that the Common Core standards insist on us trying to do. So for the purpose of this talk and looking at the initiating critical conversations, a proof is a process. So to prove is a challenge for both teachers and students. To prove is not to follow a recipe, but to discover, to solve a puzzle, to attempt to solve a problem by connecting axioms and theorems into a compelling argument. To discover is to build creatively, to involve intuition and logical thinking. And it's also to be able to communicate and explain one's reasoning. And to certify a proof is to be able to critique the reasoning of others. And this is not just from the teacher, but also from the students. Students need to be able to certify a proof. So again, for the sake of this talk, we're going to define proof as an argument which convinces people that something is true. So if I can convince you that something is true and it follows my logical reasoning based on definitions and axioms and theorems, and I am able to understand why, and you're able to understand why something is true. The other thing which I also think is important in a math classroom is that we agree with the students that once we prove a theorem, and I would like students to prove it as well, then we all agree to use it from that point on as a fact, as a stepping stone for other proofs. So, for example, once I have proven that the mid-segment of a triangle is parallel to the base and half of it, then I don't have to prove it anymore. Now I know that, and I can keep going and using it in other problems. So we distinguish 3 types of proofs: direct, indirect, and by induction. Induction is usually not used as much in the high school curriculum, but I think it's good from time to time to explain to students what it means to prove by induction. And sometimes I may use problem-solving types of problems to do that. A direct proof is what we usually do by using prior knowledge, postulates, and theorems. Direct proof is also used is using transformation, and direct proof is a proof by construction. You wouldn't necessarily see this as a separate proof, but I think it should be included as a separate proof. Any type of drawing auxiliary lines, altitudes and so on, or when we start with making a construction, then the proof that follows could be called a proof by construction. An indirect proof is by contradiction or by assumption something is true. So in catalyzing change in high school mathematics, NCTM emphasizes the use and validation of a variety of proofs. So NCTM specifies that students should look at variety of proofs. They should show their understanding using bullet list, paragraph, anything that makes sense. So for example, let's look at the following task. You're given a segment XZ and the midpoint Y. You have to prove that XZ is twice the length of XY. Please take a look at solution A for a second. And then look at solution B. Solution A is the textbook solution, and solution B is the student solution. So one would agree that solution B kind of tells us that the student does not really consider this problem as a problem to be solved in terms of providing a proof. So the student doesn't think that we need to argue this proof. On the other hand, of course, we know that the double column proof that we see, it's very well organized, contains appropriate mathematical reasoning. I mean, still, even if we consider the task worthy of a proof, the task is certainly not difficult, you would agree. And still, the textbook wrote 6 lines of statements and reasoning for this easy task. And one might wonder, how long might a proof be for a more complicated problem? And also, let's take a look at these questions. What is the big idea involved in the problem that we just looked at? So what's the big idea? Is it the idea of a segment? Is it the idea of a definition of a midpoint? Is it the importance to understand proofs? And why is a double column proof required for this problem? Why is a textbook showing this proof as an important proof or a necessary proof? And in this particular task, what are the students discovering? And what are they communicating? And what are they certifying? And I would argue that they're not discovering anything, that it's very complicated and not required to communicate that understanding in the form of a double column proof. And certifying that double column proof is taxing at best. And finally, where's the rigor? The rigor is certainly in following the proof, the double column proof, but there's no rigor in solving, if it could be solved, this kind of a problem. So for many people, double column proof is synonymous with high school geometry. In fact, many teachers cannot imagine the study of geometry without the use of double column proof. And one would assume that expectations for writing proofs would be consistent across all classrooms. These two researchers, Dimmel and Herbst, published in May of 2018 in the Journal of Research in Math Education a study where they looked at 44 high school teachers, and especially they looked at their instructional practice of certifying a proof. So the results of the study confirmed that the writing of a double column proof is most often in this classroom viewed as a direct proof taught in the high school geometry. Teachers spent an enormous amount of time teaching students how to write and check proofs line by line to make sure they're acceptable and that students provide reasons for each statement. However, teachers had different expectations for details when checking the double column proofs. teachers focused primarily on the writing of the proof and not really on the cognitive demand of the mathematics embedded in the problems. In other words, writing and certifying the column proof line by line was more important than the rigor and the discovery that we would like the students to experience in geometry. So why do we teach double column proof? Do you think it helps with organization? It certainly does. For many students, it does help with organization, but it doesn't help for all of them. Is it preparing students for college work? No. The double column proof is not used in college mathematics classes. Is it expected on a college entrance examinations such as SAT or ACT? No, it is not used on any standardized test. Does it increase mathematical rigor? It does not. More than that, it's near inefficient to use a double column proof for a multi-step problem. So then if a double column proof is not used, or is not used all the time, then what can students do to demonstrate that they understand proofs? NCTM recommends that students may want to write a narrative, a bulleted list, or some kind of explanation that they can communicate. Again, all the time, the question is, what are the students learning? What do I need to see as a teacher as evidence that a student understands? Consider the following more challenging example, and it's a very common proof of the exterior angle theorem. So take a look at the textbook solution in solution A, and then the student solution, solution B. So take a second to do that. I wish there was a way that we can communicate, as I'm sure there are a lot of things that you would like to talk about as you're looking at that. The textbook solution certainly demonstrates all appropriate mathematical reasons for each statement. However, one would agree that solution B is accessible to most students, and it may not have the right titles of the theorems involved, but it certainly demonstrates that the student understands the mathematical ideas and can apply them in solving problems. And I would certainly accept a proof like that. So let's focus on rigor. So this is a problem that I'd like you to take a sheet of paper and try it. So notice the prior knowledge. It is that the students know the isosceles triangles theorem, meaning if two sides of a triangle are congruent, then the angles opposite those sides are also congruent. And the other knowledge students need to have to solve this problem, and as a teacher, you might want to remind them, is that there are 360 degrees around a point. So here is the problem. You give an equilateral triangle ABC. On sides BC and AC outside of the triangle are constructed two squares and probably labeled. So when I teach, I wait for students to construct. I mean, you don't have to construct them. You can just, draw them by yourself. And hopefully this is a way for students to really get into the problem, even if they don't do the drawing correctly at the beginning. I want them to have an insight of what's going on. And then I'm giving you the picture. And I'm going to give you a minute to see what you can do.
Jenny, there's a request to see the question again.
Oh, sure.
So
it's very hard when you don't see the people. I know.
Yeah, that's okay. That's okay. Maybe we can pause it here just for 30 seconds so people can try to draw their own picture of it first.
Mm-hmm. Mm-hmm. Lee, are you solving it too?
Yes, I am.
So here's the picture. As you can see, ABC is the equilateral triangle in the center. And out of it are two squares constructed with length AC of the side and CB. So you have to find the measures of the angles of triangle FBE or EFB, the one that's in black. Should I go on?
Maybe give us another 30 seconds to think about it just another little bit more.
Okay. Math teachers never give up. I know that. But I couldn't not place a problem.
I believe there's a question about what we're proving. I think it's just finding the measures of the angles of triangle FBE.
That's exactly what it is. We're just finding the measures of the interior angles of triangle EFB. That's all. Okay. So here is the beginning of it. We talked about that the prior knowledge is that around a point, there's a measure of 360 degrees. So around point C, we know that there are two angles of 90 degrees. Here they are, because these are the squares. And then triangle ABC, this is 60 degrees because it is an equilateral triangle. So out of 360 degrees around this point, we can subtract the two 90-degree angles and the 60 degrees, And we came out that angle FCE is 120 degrees. Okay, so we're looking at triangle FCE. We know that this is 120 degrees. And we know that this is an isosceles triangle because these two sides are sides of same size squares. And since it's an isosceles triangle, across congruent sides lie congruent angles. So 180 minus 120 is 60 divided by 2 is 30. So this is 30 degrees, oops, and the other one is 30 degrees. Similarly, triangle FCB, this one, is also isosceles. And the acute angles, it's also isosceles, and then acute angles are 15. And finally, triangle ECB, also isosceles, 44, 40, 45, 45, 90. Okay, so the answers, I'm sure this is not considered a very difficult problem for students. By the way, this is an 8th grade problem. And it's certainly a more challenging problem in terms of the number of steps involved. It does require considerable cognitive effort for students to stay with the problems and explore it. And it would present a considerable difficulty for those of us who try to write a double column proof. Again, here is a little bit more difficult problem, which, as you see, requires at least 4 steps. I mean, these are just 4 main steps, but a lot of things to consider, a lot of things to write, and nobody's considering writing a double column proof. But it certainly, we can appreciate the logical reasoning that goes into this problem. It is an interesting problem. It's a demanding problem. It asks for application and understanding of mathematical idea rather than on restating known facts and reproducing names of postulates and definitions. So, in fact, for more complicated problems, or I would say more demanding problems in terms of length, nobody uses a double column proof. So I would like to bring in the second topic of our talk today, which is vocabulary and memorization. So let me ask you this question. How many different angle measures are there when we have 2 parallel lines cut by a transversal? And the answer is 2. Usually students would say something like, I don't know, 2, 3, 4, 5, 6, because they're looking and thinking about the corresponding, the interior alternate, the exterior alternate, all of those angles, pairs of angles that they're looking at, but they never really think about that there are only 2 angles that they need to be thinking about. And I've talked to enough high school students to see that the amount of vocabulary that they're asked to remember and restate and recall for that simple concept is kind of preventing students to understand the big ideas. So what I do, I usually use patty paper, Patty, kind of a, transparent paper. And what I do, I draw 2 lines and a transversal, and I label the vertical angles alpha and beta. So students know that the vertical angles are congruent. Then what I would do is I take the patty paper, copy the angles alpha and beta, just them with the first line and the transversal. And then I move down the petty paper for the students to see that in fact, these are exactly the same angles. It really helps for students to see that they can visually move the angles from the top intersection to the bottom intersection when you have two lines, parallel lines cut by a transversal. That helps them visualize the mathematical idea and understand what's going on. All of the vocabulary with all of those pairs of angles will come later. In fact, in many European countries, all of these vocabulary for these pairs of angles are not taught at all. Students just need to know that there are two angles, the verticals, and they are supplementary, and everything else comes into place. So sometimes we need to be thinking critically about this. In other words, what is it that the students need to know and understand out of this activity in order for the activity to be more accessible? Again, vocabulary will come. In a way, vocabulary is a little bit self-explanatory when you talk about it. But when I want the students to solve problems, and sometimes I ask them, take this, intersection and move it away from the problem so that you can see the pairs of angles on their own, it does help them to visualize the petty paper. The last topic I want us to talk about is constructions. So constructions are traditional topics. We've been taught constructions. I've been taught construction when I was a kid, and nowadays students are making the same constructions. So, for example, we ask the students to perform basic construction. Every textbook contains instructions on how to do that. Students learn to accomplish them, but they rarely see connections with other mathematical ideas. In fact, most of the time, we never come back to those constructions. Students are not asked to use that knowledge in subsequent problems. So, for example, construction of a perpendicular bisector. Do the kids understand the steps? And why do we need to know this, they ask. So constructing a right angle is one of the most valuable skills used by ancient people. I mean, they needed to construct houses, tunnels, and bridges. Embedding history in a geometry lesson will engage the interest of students. Consider, for example, how the Mayans created right angles. So let me show you a little video.
Go.
Can you see it? Okay, so this is what the students constructed. So they constructed a trapezoid made of 3 equilateral triangles. And then the red rope goes down and to the right on the picture. So this is actually a ceremonial piece of rope with 8 knots, where the knots were equally spaced from each other. And they use this to construct a right angle. And I would ask the students to prove why they've come up with right angle. And again, we can here go into, rhombus made of 2 equilateral triangles. We have a rhombus and the diagonals intersect at 90 degrees. Or you can talk about the perpendicular or the median of an equilateral triangle is an angle bisector of 30 degrees in a triangle, plus the 60 makes 90. Different ways to prove it, but it's a very interesting way for students to see what happens. And I have done several projects with my students where they have to use rope to make a right triangle. And this has been really interesting for my students. So I would really recommend it. Okay, here is another example that the way I introduce constructing the perpendicular bisector. So vesica pieces is made of two circles of the same radius. And let me show you the picture. Okay, so this is a very old picture that you can see, like an almond-shaped center of the image is called a mandorla, Latin for almond, and it can easily be seen as a grail or chalice or womb. In any case, these are two circles with radius 2 inches. So in other words, the two circles have the same radius. One of the circles is center A, the other circle center B. B is placed on circle A, so they intersect, the two circles intersect at points C and D. Okay, so you can see the picture. We draw segments AB, AC, and CB, and the students have to prove. They usually right away say that this is an equilateral triangle, and I ask them to prove their observations. So right away, they tell me that, AB and AC are radii in a circle with center A. CB and AB are radii in circle with center B. The radii are congruent by construction, so the triangle is equilateral. Then we construct the rest of the segments. We connect A, B, and D. And now they have to tell me what they know about quadrilateral ACBD. Similarly, we prove that ABD is also an equilateral triangle. Now we know that this is a rhombus, 4 congruent sides. And the angles of the rhombus are 60 and 120, the interior angles. And, students again have to write the proof. And what do we know about the rhombus? Now that we know that this is a rhombus, we know that it's a quadrilateral. We know it's a parallelogram. We know it has 4 congruent sides. We know it has bisecting diagonals, which means that CM is congruent to MD and AM is congruent to MB. And also diagonals are perpendicular. CD is perpendicular to AB. In fact, CD is a perpendicular bisector of segment AB. In fact, we have constructed a perpendicular bisector. At the same time, we have embedded the construction in a historical context, revealed its importance, and reviewed properties of diagonals of quadrilaterals. Diagonals of quadrilaterals for me is one of the essential topics before we do any kinds of constructions. So now students know how to construct a perpendicular bisector by using vesica pieces. Okay, well, I have a next step. What if I have a segment and I would like to bisect it with a perpendicular? What would be one way to do it? Okay, construct circles with same radii, which centers the endpoints of the segment. Okay, is that okay? Again, I have two circles, same radii, right? But what happened? It happened that in the first one, the circles intersected at one point, and in the second one, they didn't intersect. And that's important for students to see what's going to happen if they don't necessarily place the center of the second circle on the first one. So in other words, the students will derive the conclusion that if they would like to bisect the segment, they have to construct circles with radii a little longer than halfway the length of the segment. I'm sure that makes perfect sense to everyone. I'm just going through an example of what I do to teach this concept. Okay, but what happens if I have two intersecting circles with different radii? They do intersect at 2 points again, but it's not a rhombus that I get. I still get a quadrilateral. Well, I'm sure you see that this is now a kite. And again, the kite has perpendicular diagonals, right? So this is interesting for students to see what is the application of that. Again, I get perpendicular, but I'm not bisecting the initial segment. And finally, what if I have a segment and I just want to construct a perpendicular, not necessarily a bisector? So here is my segment. Here is a point C. I would like to construct a perpendicular through point C to segment AB. So how do I do that? Okay, so I construct a circle. Any radius would be fine. And the idea is that I am cutting part of a segment of AB so that these 2 points that are intersecting with the circle are equidistant to point C. Okay, so this is just snippets of all the things that I would like to talk to you today, and I really hope that you have some, questions for me. So here is the summary of this talk. Students learn by solving problems. For me, variety of problems. I'd like to refer to the problem we solved rather than do you remember the postulate? Do you remember the definition? Yes, postulates and definition are extremely important, but I would like them to be solving problems, exploring, discovering, trying to piece things together. Students should be able to use various proof formats. They should focus on reasoning and not necessarily memorizing, and restating axioms, postulates. Keep what you think is the minimum and have the rest come. I accept general justification and not exact wording of postulates and theorems. If they just, for example, students say that these pairs are congruent because 2 parallel lines cut by a transversal, that will be enough for me. If I very often ask students to sketch pictures to understand the problem rather than have the pictures ready and labeled for them. Yes, most of the time students do not draw correctly a picture, but that's okay. This way they understand what's going on in the problem better, and even they learn from their mistakes. I teach traditional ideas in context, and especially this past semester when we had to dig interesting ideas from the internet and using Geometry Sketchpad, it presented new ideas for teaching that I didn't think to use before. I always ask why I'm teaching this concept. What does it connect to? If I'm not connecting it and not teaching it anymore till the end of the school year, what's the point of it? What's the big teachers? And am I making students think? And at the end of the day, it's always about communicating mathematical ideas in such a way that they're accessible for most of the students in my classroom without sacrificing the cognitive demand. And I urge others to join me in a revolution of high school geometry. Thank you very much for listening to me. I am stopping sharing now.
Oh, thank you very much, Jenny, for your presentation today. I didn't see a lot of questions other than there was like a kind of active conversation going on about books and resources. One of the questions that was in the chat was, what resources do you particularly recommend? I mean, I know you mentioned using Geometer Sketchpad, and I know GeoGebra was mentioned in here as a technology resource, but do you have any other tech resources or any other book or website resources that you might recommend?
Yes, I do use all the time. Hold on, I'll show you. Just give me a sec.
That's okay.
This publication, The Art of Problem Solving, is a favorite of mine. And they have Introduction to Geometry, and they have Solutions Manual as well. It does... It is a little bit more complicated, some of the things, but you can pick and choose. All the proofs are given in the textbook, and none of them are double column proofs. So it's a really an excellent resource for any teacher. Geometry Sketchpad, I see, in one of the notes from Rose. Geometry Sketchpad is no longer supported, and it's no longer owned by anyone. And people have been giving each other passwords to download Geometry Sketchpad for free. I mean, I use both GeoGebra and Geometry Sketchpad, but I think the Geometry Sketchpad is a different level, so much better. But honestly, students are very good at GeoGebra, so either way is fine. Yes, I agree with you that... that sometimes we suck the life out of geometry. And I particularly enjoy so much problems in geometry. And, I have a couple of actually colleagues that, when I get a problem to solve in geometry, and I get them all the time, if I can't solve it right away, I send it to a couple of colleagues, and we start talking about it. And I think it's really, really wonderful to get our students to be contagious in our love for geometry. And it's not going to happen if we continue to teach the same way as the traditional textbooks. Yep, Desmos is a good place to go.
All right. I'm not sure if there's many other questions at this point. Yeah, in case people are wondering about the geometry tool in Desmos, I'm going to put a link in the chat for that. So in case you're wondering about Desmos for geometry.
Yeah, I do have a progression. In fact, I have several ideas of how the progression goes, because in the school that I worked with the geometry team, we actually did the whole curriculum. So yes, I'll be happy to share. I'm sure I have my email somewhere, correct? Listed. So
yes.
Please email me, and I'll be happy to share it with you.
Yep. Can you give us your email again?
Tsankova at RW. I'll write it.
I can put it in the chat. Yeah, or you can put it in the chat.
I'll put it in the chat.
Yes. And then there was another question after you get that typed in the chat.
Yep.
The question was, what do you think about the tendency to join algebra and geometry into one math class? Is it a good idea? So I think maybe that person is talking about the fact that, some schools have curriculums where it's more of like a math 1, math 2, math 3, and geometry is kind of integrated throughout the sequence of math classes instead of a separate class. So I think they're asking, what do you think about that approach?
So, I like the integrated approach. However, it does not have a tradition in the United States. Textbooks, even that are written, an integrated textbook, the way it's written is chapter 1 is geometry, chapter 2 is some algebra part, chapter 3 back to geometry. So again, it's not integrated in a way one would think they could be. So there are different variations. In the school that I was talking about, in the several schools in Massachusetts, what they did was one teacher taught geometry for 2 years. So let's say Monday, Wednesday, Friday, you have a geometry, the subject of geometry, and it continues throughout the 2 years. And then Tuesday, Wednesday, Thursday, for example, was Algebra 1 or Algebra 2. In other words, they had both subjects every week, taught by 2 different teachers. Each subject kind of kept its integrity for easiness, and the students got reinforcement of ideas for 2 years. So this is, again, probably the easiest way to approach this. But I really think students certainly need more than 1 year of high school geometry, especially students who are struggling with it. So that could be a possibility.
There was a question from Roberto Alvarez. What are your thoughts on teaching geometry before Algebra 1?
That's fine. Perfectly fine. I mean, again, my idea is you could teach them together for 2 years if needed, because 1 year is not enough for geometry for the concept to be retained. So you teach 1 year geometry, they'll forget the algebra. Then you have to reteach algebra again the next year. But yes, if you want to keep it, certainly geometry can go before Algebra 1. It really is not a problem. Yeah, definitely.
All right. I think that's actually about it for questions. But I thank you for being here today. And I thank you for all the people that posted ideas and thoughts in the chat. Yeah, there was one question about how would that impact students who transfer in after 9th grade? Yeah, so obviously,
you can't do, yeah.
You kind of, I feel like certain states or schools do things in a similar way based on the other schools that are around them in terms of sequencing, so that there's not that issue if they're just transferring from one local public school to another. But that's up to the individual schools, I guess, to figure out how they're going to do that and fill in the gaps that student might have in their understanding.
Absolutely. For online teaching, yes, I do online teaching. That's another question. And as you saw, I have a touch screen on my computer and a stylus. And that's how I've been using it. I use OneNote on my computer, which is free, that I can share in my screen. And OneNote creates notebooks, and OneNote is accessible for free from anything, from an Apple or from Microsoft, and you can share it as a notebook to the students as well. So if they have a stylus, they can write with you at the same time. So that was something that I used all the time. Yep. Kaylo, you had geometry and algebra every year starting 5th grade. Absolutely, I agree. It's better and gives us more time to think, to understand, to remember ideas. Please email me with additional questions, or if I can help you with anything, it would be my pleasure.
All right. Thank you for being here today, and I thank all of you that showed up for this special edition of the Global Math Department. As I said, we typically don't have any sessions in July, but we happen to have one this year since Jenny agreed to do this in July, since we had some tech issues earlier when we tried to do this in June. So thank you very much for being here. And the recording will be posted in about 24 hours.
Thank you for facilitating this.
Oh, you're welcome. You're welcome. Yep. Our next Global Math Department sessions will begin in August. I believe we have people scheduled starting the 2nd week of August. So I hope to see many of you here back here in about a month. Have a lovely afternoon, evening, or morning, wherever you are.
Yes, everybody have a wonderful rest of the summer and beginning of new school year.